Projects like ChatGPT and Stable Diffusion have renewed the interest of many in machine learning, myself included. I made a few videos on how to run open source language models and even how to replace the OpenAI API with an open source alternative. I always felt I don't have enough grasp of the theory behind it all, so I started playing with Jupyter notebooks and learning a bit. So this video is about machine learning, the first steps. We're going to use Kaggle.com. This is a website you can run Jupyter notebooks online and share models, code, and datasets. It's free to use, and it even has GPUs to do some heavy working. In this first part, we're going to cover the basics of machine learning. And the second video, we're going to apply DevOps practices to take the notebook and put it into productions using things like data version tracking and continuous integration. So be sure to subscribe or follow us so you don't miss the next part. Before starting, let's review a few words we are going to need during this learning. First, we have the model. The model is a mathematical representation of a process we want to predict. Inference is the process of making predictions using a trained model. Features are the input variables used to make predictions. They are commonly represented with an uppercase X. For example, if we are using a computer vision model, the features are the images we are using, the information extracted from the images to make a prediction, for example, what type of image it is. Prediction is the output of the model, is the response the model gives to a given data. Epoch is a fancy word for iteration, is the single path of the training process through the entire data set. So we can have 1, 2, 3 more epochs during our training process. And loss is the measure of how well the model predicts when faced with new data. We want the loss to be as low as possible. A model with less loss is a better model. We can think of machine learning in two big groups. On one side, we have traditional machine learning. In this type of learning, we know the algorithm. We know the steps required to make a prediction. An example of this is finding a regression function. This is the line that best fits the existing data. We know the mathematical formula. We can use statistics to make the prediction. But what happens when we don't know the algorithm? Examples of this are seemingly easy things like seeing, recognizing an image, or hearing a pattern and recognizing words, or thinking. These are all examples that are easy for us humans, but we don't know the steps required for a computer to reproduce. For this type of problems, we use a different approach. We use neural network. A neural network is made of several layers. These layers consist of neurons interconnected one to another. We have an input layer which receives the input data. Then we have the output layer that produces a prediction. In the hidden layer is where most of the complex computation work. They take the inputs and process them through a series of weights or parameters. These are adjusted during the training phase. This is an iterative process where we feed a lot of data to the model, we get the results, and then we calculate the loss. This is the difference between the predicted values and the actual value. These are used to adjust the weight and the process repeat. Basically, we are teaching the computer how to interpret the input data, like for example images, until the output is accurate enough for our use case. To get started, let's create an account on Kaggle.com. We can do this for free. It's a good idea also to verify the account. We have to go to settings and phone verification, where we put a phone number and get an SMS to verify the account. For this trouble, we get internet access in our notebooks, which is very useful to run our examples. Finally, we can go to create and new notebook, and here on the right side we can enable internet access. We can also activate GPUs and add data and models. We are going to use these features next. I'm going to leave links to all my notebooks so you can play with them. The first example is going to be a traditional machine learning. I have a CSV with housing prices for the California region. As you can see, we have a bunch of columns here, latitude, longitude. We are going to try to predict the median price of the house based on several features. The first thing we have to do is to clean up the data, and for this I'm going to simply delete all the incomplete data. We can do this first by reading the CSV and then running drop NA with axis 0 means delete the rows that have empty values, and we are going to replace the data frame in place. So after running this, we're going to see how many empty rows we have. As we can see, we have no empty rows, so the data is complete. For the next step, we can visualize a little bit the data by plotting that into a real world map. And as you can see, we have the prices for all these regions, and we have a scale here with a gradient. First step for training is to select the features. Remember, the features are the parameters we're going to use as predictors. So we need to pick columns that have good predicting value. This is a little bit of trial and error. So here we're going to first define the value we're going to predict, which is the median house value. This is what we want to get out of the model. And then we're going to define the columns that are going to be features. I selected these 5 columns and I initialize the X variable with all these rows and columns. The next step is to split the dataset. One common problem when training, it's called overfitting. It means that the model has memorized so much the data that it performs very well when faced with the training data, but performs badly when faced with new data. So one way to avoid or to work around this problem is to split the dataset into 2 parts. We're going to generate a training dataset and a validation or test dataset. For doing that, we can use a function in the scikit-learn framework. It's called train test split. This function takes the features, the target, that is the values of the prices. Then we can define how many rows to set apart for validation. Reserve 20% of the dataset for validation. This 20% will not be used for training, will be reserved for testing. And then random state is one way of making the training more predictable. If we keep this number the same, the split will always be the same. The function returns a training feature set, a training test set, and the target values for the test and the training. So we're going to create the model as a decision tree, and then we're going to use the fit function and feed it the training features and the training target. The result is a decision tree object. So how do we test the model? We can take the features in the test and use model predict. This will give us predictions. These are prices the model thinks are correct. Then we calculate the mean absolute error. This is how much the target data, the actual target data, and the predicted target data are one away of the other. And when we take that, we find that we have a mean absolute error of $43,000. Let's try to find out if we can do better. One of the problems we face commonly when training a model is overfitting. It means that the model has learned too much of the patterns in the training dataset and does badly when faced with new data. As I said, one way of avoiding overfitting is by separating the dataset into 2 parts and hiding one part from the model. But another way of doing that is by finding the right size of the model. In this case, this is a decision tree. And decision tree can have a lot of levels, a lot of leaves. So what is the right number of leaves of the split points in the tree to capture the complexity of the problem? If we pick too few split points, the model will not be able to capture all the complexity. Now, if we pick a model that's too big, we run into the chance of a model that is too sensitive. It picks up spurious data. It learns patterns that are not real, that are aberrations in the dataset. So there's a perfect size of the model that we need to find by experimentation. So for this type of model, I can control the size by changing the leaf nodes, which is controls how many levels the decision tree has. I have created a function that takes this and is a parameterized model. I train the model with this parameter, and then I return the mean absolute error. So I can use this to compare 4 different sizes, 5, 50, 500, and 5000 leaf nodes, and we can find the optimal size for our dataset. The best option here is clearly 500 leaf nodes. This brings us the lowest error so far, which is $38,000. Another method we have to make a better model is to use random forest. Random forest are various decision trees that are trained in parallel. They each make a prediction and then we average the result, and this usually brings a more accurate result. In this case, instead of using the decision tree regressor, we're going to use the random forest regressor, and it's very much the same. We initialize the model and you call fit with the training features and the training target. And as you can see, when we calculate the mean absolute error, we get $31,000 of error, which is less than our best decision tree. Now let's see a different kind of machine learning. We're going to train or fine-tune a neural network. In this case, it's called a convolutional neural network, which is has good performance on computer vision. Convolutional neural networks are used mostly for computer vision because they can extract features from the images. For example, we can take the borders, the edges of the images, the contours, and this all became features that can be used to say what the model is seeing. This type of networks are made of two parts. The base is the part that extracts the features, that processes the image and extracts the features. The other part is the head. The head takes the features and assigns them into a category. For example, it's a cat, it's a dog, it's a car, it's a giraffe. The convolutional neural network has 3 steps in the base. First, we have the convolution, which uses a set of filters that slides over the image. The process transforms the input image into one or more feature map, highlighting certain features of the image. The second step is detect. This introduces nonlinearity into the model, allowing it to do more complex patterns. The final step is condense. It downsamples the representation of the image into less pixels, reducing the number of parameters and making the computation more efficient. For this fine-tuning example, we're going to take a pre-trained base model called ResNet34 that is able to extract features from the image, and we're going to create our own head, which will map these features into either cats or dogs. The fine-tuning process creates the head and attaches it into the pre-trained model, creating a new model that's specialized for cats and dogs. So let's see how it works. I have added the Oxford Pets dataset into my notebook. It contains about 7,000 images of dogs and cats. The most important thing is that cats begin with an uppercase and dogs with a lowercase, so we can use that to label the image as a cat or a dog. We don't really care about the breeds in this example. The first step is to load the data. We're going to pass the parameter with the path with the images. Then we define this labeling function which returns true for cats or false for dogs. To load the data, we are going to use the data loader. This is a function in the Fast AI framework that works on top of PyTorch. We are going to supply the path with the images. We're going to set 20% of the images for testing, for validation, a random seed that's constant, the labeling function, and then a transformation. We are going to resize all images to a square 224 by 224 pixels. This will help accelerate the process. So basically the image data loader combines the split with the labeling and resizing. We combine everything here. By running valid show batch, we can see how the data has been labeled, and we can see that cats are indeed true and dogs are indeed false. Fast AI made things very simple. We use vision learning to start the model. We pass the images. Then ResNet34 is the base neural network already being pre-trained. The loss is going to be error rate, so we want to minimize that. And when we run fine-tune, with one epoch, we're going to go one time over the training dataset. So this is going to take about 1 minute or less because I have enabled the GPU here. So this is going to run very fast. We can see the GPU here activity and the CPU and the RAM. So it took less than a minute, and we have here the error rate and the loss. Now let's see how well the model does with the validation set. Fast AI has the show results built in, which automatically shows some examples. So running this will show us some of the images with the labels. So we see all these correct predictions. Next, we can calculate the confusion matrix. So the confusion matrix show us the false positives and the false negatives. Everything in the middle diagonal are correct guesses. So this is all the dogs that were correctly detected and all the cats. But we have cats that were detected as dog and some dogs that were detected as cats. In total, we have 5 images in the validation set that were misclassified. To see what images have been misclassified, we can call plot top losses. We can see here all the misclassification. This is, for example, a dog that was classified as a cat and the other way around. There are some cases in which the classification is correct, but the level of confidence, which is this number here, is too low. You may run into an example that a cat was classified as a cat, but maybe with only 50% confidence. That's an error for the model. And so finally, to see the model in action, I'm going to run this cell. This cell is going to download 2 images from Wikipedia. The first is from a dog, and then the other one is from a cat, and I can see the results. The first one is a dog and it has good confidence that it's a dog, and the other is a cat and also has good confidence it's a cat. So that's a way of testing the model with external data and to see it in action. In this case, we can see the code required to make the inference. So that's all for today. I learned a lot doing these notebooks. I hope you liked them. If you did, please like, subscribe. We are going to do a second video where we take everything we did manually and automate it using some DevOps tool. We are going to use continuous integration, data version tracking, machine learning pipelines to make this process automated and more reliable, so we can take something that's an experiment and make a product that is releasable and can be used by the end user. Thank you for watching and see you on the next one.